Alright, thanks for watching and welcome to this very important video about diagonalization and eigenvectors. Because so far we've seen that eigenvectors are something algebraic. For every eigenvalue you find a corresponding eigenspace. But it turns out that eigenvectors tell us something very geometric as well about your linear transformation. And really the best way of describing this geometry is with the notion of direct sum, which let me define it now. And there are many different definitions. I'll use the one that's slightly easiest to deal with. So we say that a vector space is a direct sum of subspaces. So W1 O plus, etc., O plus WK, where Wi is a subspace of V, if and only if the following two things are satisfied. First of all, why is it called a direct sum? Because in order to be a direct sum, V has to be a sum of those spaces. So V is the sum of W1, etc., up to WK. What does it mean to be a sum of subspaces? It means that any element in V can be written as the sum of K elements, where each of them, the first element is W1, the second one in W2, etc., and the last one in WK. So it's kind of an analog of spanning, except you're just using sums, not linear combinations. But the problem is this is not enough to define what's called a direct sum, because look, for example, take the x-axis, which is the span of 1, 0, the y-axis, which is the span of 0, 1, and also the axis y equals to x. Then the problem is, we don't have, well, it is true that R2 is a sum of those three things, but it's not very efficient. We can kind of eliminate this y equals to x-axis. And the idea is, because, for example, 1, 1, this vector, we can write this as a sum of three things. Either we can write it as sum of 1 plus 0 plus 0, 1 plus 0, 0, where the first one is on one axis, the second one and the second one, and the third one on the other axis. Or we can write it in this way, 0, 0 plus 0, 0 plus 1, 1. Where this is on the first subspace, this is on the second one, this is on the third one. So in some sense, we don't have a uniqueness statement, but for direct sum, we do have an analog of uniqueness, which is just as follows. If you have W1 plus etc. plus WK gives you the 0 vector, where those are little vectors, so where each little Wi is in Wi, then the only way this could happen is if each of them is 0. Then W1 is 0, WK is 0. So if each vector sums to 0, then the only way this could happen is that the vector itself is 0. And for example, we don't really have this here because you could have 1, 0 plus 0, 1 minus, I guess plus if you want, minus 1 gives you the 0 vector, but not each of them is 0. So this is the correct definition of direct sum, and it kind of says that W1 is independent of the other ones, W2 is independent of everything else. And hopefully you can convince yourself that this is a very relaxed analog of bases. This is like V is spanned by those subspaces, more or less, and this is kind of an analog of linear independence, except we're dealing with vectors here. All right, now why is this important? because it really relates to diagonalization in the following sense. So here's the main theorem that I'll prove today. If, again, suppose that the characteristic polynomial splits, so t has eigenvalues and eigenvectors, then we say t, so the theorem, t from v to v is diagonalizable which means it's there is a basis of t, of v corresponding of eigenvectors of t, if and only if t is the direct sum of its eigenspaces. Lambda 1, direct sum, lambda k, where lambda 1 up to lambda k are the eigenvalues of t. I guess distinct eigenvalues. Of t. And remember what our goal was. Our goal was, sorry, that shouldn't be t, should be v. If and only if, again, an operator is diagonalizable, at least in the finite dimensional case, if and only if the vector space itself is a direct sum of the eigenspaces. So in other words, if and only if you can decompose your vector space in terms of the eigenspaces. And remember what our goal was. Our goal was to describe linear transformations geometrically. Well, it turns out this gives you a very nice geometric description. And I have done another video on this, by the way, where I give some geometric flavor in, for linear transformations. But why is this a geometric description? Because heuristically, you should think of each eigenspace as an axis. Even though it might not be a one-dimensional axis, might be a two-dimensional one or something. And what this is saying is, if your linear transformation is diagonalizable, then you can find an axis of eigenspaces. So let me just give you a little example. And that's the one I talked about before. So 1, 1, 4, 1. So it turns out you can find the eigenvalues. Lambda 1 is -1, lambda 2 is 3, and you can find corresponding eigenspaces. So I think E of lambda 1 is the span of, I think 1 minus 2. And E of lambda 2, it's the span of 1, 2. And what is this saying? So it turns out, yes, we can have a, so first of all, it's diagonalizable because there is a basis consisting of two eigenvectors, which is 1 minus 2 and 1, 2. And what this saying is, R2 can be written in terms of those eigenvectors. So in other words, there are two axes, one that's spanned by 1, 2, which looks like that, and the other one that's spanned by 1 minus 2. Oh, that's correct. Let's see. 4, yeah, okay. And then there's 1 minus 2. Let me see. This one is disappointing. So again, in other words, what you can say is R2 has two different axes. One which is directed by 1, 2, the other one directed by 1 minus 2. I guess I should write this way. It goes like that. 1 minus 2, and essentially every vector in R2 can be written somehow uniquely in terms of those two axes. So, in other words, every vector can be written as a sum of two vectors, one in this axis and one in this axis. And so in this case, we can say that T is diagonalizable. So in other words, T is diagonalizable if you, and only if, you can find axes consisting of eigenvectors. On the other hand, what does it mean to be not diagonalizable? for example, the very famous example is this one. It's 1, 1, 0, 1. Then you can check there's only one eigenvalue, which is 1, and just one eigenvector, which is a span, I think, of, let's see, 1, 0. Then it turns out, no, in this case, you cannot write R2 in terms of the eigenspaces, because here there's just one axis, right? The x-axis. And the question is, how can you write R2 just in case in terms of the x-axis? So in that case, we say it's not diagonalizable. So in other words, again, to emphasize it again, operator is diagonalizable if and only if you can write the vector space as a direct sum of the eigenspaces. All right, and now with this motivation, let's prove this. So let's do I think there's an easy direction and a hard direction. So let's do the easy direction first. So suppose we have a direct sum. V is the direct sum of eigenspaces, and let's show T is diagonalizable. So what we need to show is that there is a basis of T consisting of I keep mixing those up. So what we need to show is that there's a basis of your vector space consisting of eigenvectors of T. But we have those eigenspaces here. So let beta 1, and again there's a lot of notation, so we want to say V1 up to V, let's say M1, where M1 is a multiplicity of the eigenvalue, but because we're doing it for each of them, we need an extra index at top, which is, let's say, V11. So let V blah 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 be a basis of E lambda 1, and beta 2, same thing, but with the second eigenspace, so V21 up to V2 M2, be a basis of E lambda 2. And by the way, those are disjoint because it's not possible that you have an eigenvector for one eigenvalue and for a different eigenvalue at the same time. So that doesn't make sense. And lastly, up to beta k, which is a basis for E lambda k. Now the question is, you have the bases for each little eigenspace. So again, in terms of our picture, if you have, let's say, E lambda 1 and E lambda 2, you can have a basis here, beta 1 of the first axis, beta 2 of the second axis, and how can you find a basis of eigenvectors? Well, just put all of them together. So I'm claiming that if you put all of them together, beta, which is defined as beta 1 union beta 2, union beta k, it's a basis of the whole space V. And then, by the way, we would be done, because look, we would find a basis of V, and notice all the elements here are eigenvectors of T. So we would find a basis consisting of eigenvectors of T, which by definition implies T is diagonalizable. All right, so we need to show that it's linearly independent and that it spans. Okay, so first of all, let's show beta spans. And this is a beautiful exercise in just using the definition of direct sum. So let V be in V. And remember, V is the direct sum of the eigenspaces. So in particular, it is the sum of the eigenspaces. Lambda k. Then what this means is V is the sum of vectors, each of them being in that eigenspace. So then V equals to W1 plus W2 plus plus WK. where each wi is in E of lambda I. But here's the thing. For each individual eigenspace, we have a basis, right? Because we know that beta I is the span of E lambda I, which is just the span of Vi1 up to Vi mi. So in particular, what do we know? We know Wi is just a linear combo of those vectors. So that equals to A. So Wi, it's AI, lots of indices. I1, Vi1, plus dot dot dot, plus AI, Mi, Vi, Mi. And lots of I's. So it's just like this spider or something with lots of I's. So what do we get? We get that this AI1, Vi1, plus dot dot dot, plus AI, Mi, Vi, sorry, everything is with 1, because W1. So A1, 1, V1, 1, plus dot dot dot, plus A1, M1, V1, M1, plus A2, 1, V2, 1, plus dot dot, plus A2, M1, A2, M2, V2, M2. So you see, all we're saying is we have a linear combo of V1 up to Vm's, but for each eigenspace. So plus dot dot dot, plus this last one, I think AK1, VK1, plus AK, MK, VK, MK. I know, it's a huge sum, but that's precisely what we want. Because notice, those vectors, they're all in beta 1. Those vectors, they're all in beta 2. Those vectors, they're in beta k. So what do we get? We actually get a linear combo of all those vectors. And what did we call all those vectors? Well, precisely beta. Beta is just a union of all those things. So, in fact, this is in the span of beta. So in other words, an arbitrary vector in V is in the span of beta. So beta spans V, and then we're done with the spanning part. So beta spans V. So that's one thing. Then let's show it's linearly independent. Which means we have to rewrite this. So but it's nice. So I think it really illustrates, the two definitions of direct sum. The sum part helped us with spanning. The other thing, the direct part, I guess, helps us with linear independence. So suppose, again, A11, V11, plus dot dot dot, plus A1M1, V1M1, plus A21, V21, plus dot dot dot, plus A2, M2, V2, M2, plus everything, plus AK1, VK1, plus dot dot dot, plus AK, MK, VK, MK. Suppose all this gives you the zero vector. Because that's just a linear combo of every element in beta. Because remember, beta is beta 1 up to beta k. So what this says is, suppose you take a huge linear combo of all the vectors in beta and you find 0. Then I'm claiming all the coefficients are 0 because this one, call this W1. This one, call this W2, etc., etc. And this one, call this WK. Now, in which space is each wi? Look, here you're taking linear combos of vectors in E of lambda 1. E of lambda 1. But for a given eigenvalue, the set of eigenvectors forms a subspace if you add the 0 vector. And in particular, this is just a linear combo of vectors in E lambda 1. So this is in E lambda 1. This is in E lambda 2. This is in E lambda k. So what do we get? We get that W1 plus dot 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 plus WK equals 0. This just simplifies. And each Wi is in E lambda I. So, by the second part of direct sum, we get by assumption that each of those is 0. Wi equals 0 for all I. Again, that's by 2. By 2 of direct sum. It's kind of the uniqueness statement. I don't know. I keep writing what's on my mind. No, not direct uniqueness, but direct sum. All right, very good. So what do we get? We're essentially done because we basically get each individual one is also 0. So, in particular, we get that AI1 VI1 plus dot 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 plus AIMI VIMI equals 0. But look, those are just vectors in beta I. But beta I, which is VI1 dot 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 VIMI, we know this is linearly independent. Just because we chose a basis for E lambda I. So in particular, for every I, we can conclude that each of those coefficients are 0, just by linear independence. So AI1 equals 0, AIMI equals 0. And because I was arbitrary, we get the first round of coefficients is 0, the second round of coefficients is 0, and the last round of coefficients is 0. So everything is 0, and therefore we get that beta is linearly independent. So for all I, yeah. So we get that beta is linearly independent. And therefore, what do we get? We get that beta spans V and is linearly independent. So beta is a basis of V, and the point is beta only has eigenvectors, so we get a basis of V consisting of eigenvectors of T. So that's good. In other words, if we find that V is a direct sum of the eigenspaces, then we can easily construct a basis of eigenvectors of T. Now, let's do again, if you're enrolled in my course, that's the part you need to know. The next one is more for fun. Now let's show the converse. Now let's prove the forward direction. So let's show that if T is diagonalizable, this implies that V is the direct sum of the eigenspaces. E lambda k. And by the way, so as I said, we assume that the characteristic polynomial of T splits, which means it's a product of linear factors. In particular, we know in this case T has eigenvalues, and without loss of generality, they're all distinct here just by grouping all the same eigenvalues in those eigenspaces. All right, and what do we want to show? So first of all, what do we know? Because T is diagonalizable, we know that beta, there exists a basis of V of eigenvectors of T. So no, there is a basis beta, which is V1 up to Vn of V corresponding to eigenvectors of T. So I guess not correspond, but of eigenvectors of T. Of T. But here's the main problem. This basis itself is kind of jumbled up. So beta, well, it might look like V1, V2, V3, V4, V5. You'll see why I'm doing that. Up to Vn. Now look, the first one, okay, it might correspond to the first eigenvalue. V2, it's possible that it also corresponds to the first eigenvalue. And then V3 might be the third one, the second one, and then V4 might also correspond to the first one, and then V5 corresponds to the third one, V6 to the second one, etc., etc. The problem is those eigenvectors aren't really ordered by the eigenvalue, but that's not a big problem because notice you can always switch those. So you have V1, V2, V4 might correspond to lambda 1, lambda 1, lambda 1, and then V3, V6 might be lambda 2, lambda 2, and then V5 might be lambda 3, up to Vn. So you can always rearrange your basis so that it corresponds to the correct eigenvalue. So in particular, what we can do, if you want, if we define beta I to be the part of the basis that corresponds to E lambda I, we can actually rewrite this. So, in other words, we can write beta as, if you want, V11, V1 M1, V21, V2 M2, up to Vk1, Vk Mk. Where each of those, the first set of vectors corresponds to E lambda 1, the second set of vectors to E lambda 2, and the last set of vectors of E lambda k. And I don't think we'll like introduce a new eigenvalue because otherwise we would have a new eigenvalue of t, and then that's a problem. Also, there's this other fact which I'll talk about, that otherwise we would get a new linearly independent vector, and that might be an issue. All right, so this is good. So we know that beta can be written in terms of those eigenspaces, and using this fact, I can show that V is indeed the direct sum of the eigenspaces. So let's first show the first part of direct sumness. Let's show that V is the sum of E lambda 1 up to E lambda k. But that is not a problem just by the way I define that basis. So let V be in V, arbitrary. And then since now beta, which we've rearranged it correctly, V11 up to V1M1, V21 up to V2M2, etc., etc., Vk1 up to Vkmk is a basis. We know that V can be written as a linear combo of those vectors. So A11 V11 plus plus A1M1 V1M1 plus A21 V21 plus plus A2M2 V2M2. Crazy number of indices, but Vk1 V1 plus AKMK Vk MK, that's a K here, And the point is, I know it's like a huge linear combo, but each of those vectors are in E lambda 1, just the way I rearrange the basis. So this is in E lambda 1. And let's call this W1. And this is W2, which is in E lambda 2. And this is up to WK, which is in E lambda K. So what do we get? We get that this arbitrary vector, it's in W1 plus dot 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 plus WK, where Wi is in E lambda I, and that is literally the definition of being the sum of those vectors. So in other words, we get that V is E lambda 1 plus dot 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 plus E lambda K. So that is good. That is the sum part. And now let's show the direct sum part. And so now in particular, all right, so let us suppose that we have W1 plus dot 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 plus WK equals 0, where each Wi is in E lambda I. And let's show that each of those vectors I equals 0. And if you want, I mean, technically, the reason this follows is because there's this fact that says if you have eigenvectors corresponding to distinct eigenvalues, then they're automatically linearly independent. And because this is kind of a linear dependence relation between the two, we actually have that. It's we actually get that each of those vectors is 0. But if you're not convinced, let me give you a quick induction proof of this. So if you want to do induction on K, well, for the first case, there's nothing to prove because W1 is 0. Okay, and for the induction step, so for I, it's from 1 to K. For the induction step, assume it's true up to K minus 1, and let's show it's true for K. So suppose W1 up to WK gives you 0. Well, apply T to this. T W1 plus WK. It's T of 0. So we get TW1 plus dot 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 plus TWK. That is 0. So lambda 1 W1 dot 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 plus lambda K WK equals 0. That's on the one hand. On the other hand, multiply this by lambda K. So then lambda K W1 plus dot 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 plus lambda K WK equals 0. Then you can just subtract the two. Then you get lambda 1 minus lambda K W1 plus dot 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 plus lambda K minus 1 minus lambda K WK minus 1 equals 0. So those things, they cancel out. And what we get then is, those are all of those, you see, are in E lambda I. So this is in E lambda K minus 1. It's in E lambda 1. And what we get is that each of those individual vectors is 0. So lambda I minus lambda K Wi equals 0. By the induction hypothesis, since this is non-zero by distinctness, we get Wi equals 0 for I from 1 up to K minus 1. And what about the K part? Well, now we know that the head of this sum is 0, and therefore it follows that this last part is 0 as well. So it is true that if we have the sum of vectors that gives you 0, each of those individual vectors is 0, and therefore we get that this is done as well. And in particular, it explains why when we have this basis here, we're not skipping any new eigenvalue, because it's possible that this is enough to describe all the eigenspaces, but if we have some different eigenvalue, let's say E of mu, which was not in this list, then the problem is, what this is kind of saying is that if we had another vector to that list, because it's not in the previous ones, the new one will be linearly independent and it won't be a basis anymore. So I think this is a proof. Correct me if it's not. But yeah, therefore we have shown that if your eigenspace is, if T is diagonalizable, then T is also a direct sum of the eigenspaces. And this just concludes everything. T is diagonalizable if and only if V is a direct sum of its eigenspaces, which again gives us a nice geometric description into the magic of eigenspaces and direct sums. Alright, thank you so much. If you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.